the center of mass, when you have a collection of particles, of masses that are connected and that will rotate together as one single unit, we can figure out that point that they're going to rotate about based on how the masses are distributed. If we're dealing with just a stick, the center of mass is going to be in the center of a stick. If it's a ball, the center of mass is going to be in the center of a ball. If we're dealing with some particles that are distributed about, some and connected like as a square, what we need to do is to look at the masses of each particle compared to where they are in reference to each one. So we basically need to look at each one's XY coordinates. And then we can figure out where the center of mass, like if all these were the same masses and all these were the same distance apart, we can do a calculation and the center of mass is going to be, hopefully not too surprising, right in the middle of those four particles. Now the calculation to do the center of mass is shown right here. That gives us the x coordinate for the center of mass. And what we need to do is we pick an arbitrary reference point. It doesn't matter where it is, but we pick some reference point and we say this is our 0. And so in this example here, I might pick this line right here, this point halfway between those, as my origin. And then I do the calculation based on the origin. Like mass 1 is how far away along the x-axis from the origin, and that's going to be in a negative direction, so I would capture that as, in my example here, if this distance is L, M1 is 1/2 L from the origin, and since it's in the negative direction, I'm going to put a negative 1/2 L. And we just continue with that. So I'll tell you what, I hadn't planned on doing this, but what the heck. Let's take a look at it and let's figure out the center of mass for that system here. And I'm just going to call all the masses the same, and I'm just going to call them all a mass of M. And so what I'm going to have is simply M, my mass, 1, times the distance from where it is to the origin in only the x direction, and that's negative 1/2 L. I'm going to add to it my next mass, M2, which just is mass 1. It's also 1/2 L from the origin, except I'm in the positive x direction. I'm going to add to it my x coordinate for mass 4, which is just M, and this is, if I'm just extend this down, this is negative 1/2 L away from my origin. So give me about 15 minutes. Talk to somebody outside the door. And so this mass is going to be negative 1/2 L. Similarly, M3 is going to be pretty similar, not pretty similar, identical to M2. It's M over times 1/2 L. That's what this top part is equal to. The bottom part, I'm just going to add up all my masses. Mass 1 plus mass 2 plus mass 3, yada, yada, yada. Since I have 4 masses, each one is M, that adds up to 4M. And so, negative 1/2 L plus 1/2 L, these two terms are going to end up canceling each other out. That's a 0. Negative 1/2 L, these two terms are going to be canceling each other out. So I end up with 0 over 4M. Trandy, what's that on your calculator? Excellent, 0. So my x-coordinate of the center of mass is 0. So this is my x-coordinate. I'm along this coordinate line. Now we're going to look at the y-coordinate, and I'm going to keep my origin right here. And I'm going to go through the same process. I'm going to go through the same process with my y coordinate that I went up here. The difference being I'm going to take this point and I'm going to look at the y direction. How far in the y direction from my reference origin are each mass? So let's start it off. We've got mass 1 is along it's 0 distance in the y direction from my origin point. So I'm going to put 0 here. Mass 2 is the same thing. It's 0 distance from my origin point. So I put a 0 there. Even though they're on my y-axis, I've got to account for their masses. Even if it's a 0, I'm going to include them in the calculation. And you'll see why that is in just a second. For mass 3, it is in the negative L direction down. So I'm going to say m times negative L. And then my mass 4 is the same thing. It's in the negative L direction down. That gets to be a negative L also. This is over the total mass of my system, which as before was 4m. Even though these two masses work out to 0, I include it in the denominator as the total mass of my system. That's an important point. That's one thing I kind of screwed up on the other day. So that's 0, 0. This works out to be negative 2m times L over 4m. The m's cancel out. That's a 2. And this works out to be negative 1/2 L. And so my y coordinate, my center of mass for this problem is at, here's my x coordinate, 0. Here's my y coordinate, negative 1/2 L, which puts me 0, negative 1/2 L. So here's my center of mass, exactly where I thought it would be because of the symmetry. I want to do another problem where it's a little bit different. And this was the example problem I was starting yesterday, or Friday, since if you're seeing this on Monday, I wasn't here Sunday. But I want to finish this so that we have a good understanding of how to do it, because there's some problems in Chapter 12 that I'm going to want you to work on, and one of them, I believe, is a center of mass problem. I've got 3 masses. I've got a sphere of mass m. I've got a sphere of mass 2m, and we have a bar that's a mass 3m, and L's and 2L's and 3L's are my distances there. First thing I need to do, I need to pick my arbitrary origin point, my arbitrary reference point. And just like what I did the other day, I'm going to pick it right in the middle of my bar. When we have a bar like this, we can assume all its mass is concentrated right in the middle of the bar. And so when I do my center of mass calculation, I'm going to treat it like all the mass is right here at the green dot for that bar. And we'll work the calculation. So to get my x coordinate, I want to take the mass times its x distance from my origin. And so the mass, and I'm just going to start with that one, and then I'll go to this mass, and then I'm going to go to mass number 3. So I have a mass of m. It is negative 3L over 2 away from my coordinate. It's half the distance away, half of 3L. Kind of an awkward way of writing it. So what? My next mass is the bar. It's a mass of 3m. Its location is at the origin. So I'm going to put in a 0 right there. My third mass has a mass of 2m. And it's located at half of the 3L distance. So I'm going to put 3L over 2. distance away. This is a positive distance. This is in the negative direction. That's why I put the negative sign. Divided by my total mass. M plus 2m plus 3m is equal to 6m. And so my x-coordinate for the center of mass works out to be negative 3L over 2m. That's a 0. Plus, those 2's cancel out. I have 3LM over 6m. So my x-coordinate is going to be, let's see, this is 1, that's 1.5 L negative. So I'm going to have 1.5 LM over 6m. M's cancel out. The 1.5 over 6 is 0.25 L. The thing that I failed to do the other day was to include the bar mass right here, and that was my mistake. You have to include it. So the x-coordinate for the center of mass is somewhere along the 0.125, the positive 0.125 L. Let's say it's somewhere along that line. Now I want to look at the y-coordinate. I'm going to keep, and I'm going to look at the y-coordinates. I'm going to keep the same origin point, and I'm going to just kind of repeat the process. My first mass is m. It is a negative L distance below my y origin. So I'm going to put m times negative L plus 3m. My rod is still at the coordinate. It's at the origin. So once again, I'm going to put 3m times 0. It seems kind of silly to include this 0, but I'm including it because I want to make sure I include all the masses. Even though this coordinate is 0, it factors into my overall position of the center of mass because I have to include that mass in the denominator. Third point is the 2m mass, and that's negative 2L below my y-axis line. Once again, divide by my total mass, which is 6m. And this works out to be negative ml minus 4ml over 6m. That's negative 5ml over 6m. My m's cancel out. Negative, I'm just going to be lazy, negative 5,6L. So my coordinate, my center of mass coordinates for this system, for these two spheres and this rod, is at x is 0.25 L, y is negative 5,6 L, which I said my dotted green line is about my x-axis, and if I go negative 5,6 down, it's going to be right about there. So this is negative 5,6 L. This distance right here is 0.25 L. And so that's would be my center of mass for this system. Okay, let's see. Any last minute parting thoughts? I know this was pretty quick. You have the opportunity to see it again because I know everyone wants to watch it because it's just so fascinating. This particular problem, if you have the Princeton Review book, this particular problem is, I believe, example 510. Feel free to take a look at it. I have, I think, one of the sample problems in Chapter 12 that I asked you to do gets into this a little bit. So I'm going to probably have you take a look at that also. Practice that. And some of the practice problems I'm going to have you doing this. On Wednesday, when I get back, I'm going to give you a quiz. The quiz is going to be over some torque problems and center of mass problems. So make sure you practice this stuff. Okay. I hope you got it. If not, replay it. If not, copy it, watch it later. Hope to see you Wednesday.